So, hello everyone, and welcome to this weekly session that we conduct, Ask AuxEn Anything. And as you all know, that this is an online platform for civil structural engineers to interact with us and ask their doubts or queries that they may have related to any steel design or RCC design concept or any project that they are doing or construction site issues. So, this is the 54th such episode that we are conducting. And let us begin with the queries that have been put for this week. So, first, we will take the queries from the Google form, and then I will take the queries from live comments. Okay. So, the first query is from engineer Rohit Kashyap. He is from Guwahati and he's a working professional. So, he is asking, uh, I'm just pasting the query. And let me share my screen. Yeah. I hope the screen is visible. So he's saying in a building, the dead load and live load is constant. So the seismic weight is also constant. Let us take four shear walls and calculate the time period and then base shear. And then if we increase the shear walls to 8, the time period reduces. So base shear increases. Theoretically, it is okay. But if we increase shear wall, why are we designing for higher forces? So, see, as you all know, I mean, his what is his query is uh, his query may be a query which many of you might have. He is saying, let's say this is the plan of your building, and you have planned some shear walls. For example, uh, I hope the screen is visible to all of you. So let's say there were shear walls that were planned like this. Okay, four walls along X and maybe four walls along Y or other direction also. I'm not drawing the walls in the other direction as of now. So there were four walls along a particular direction, and he's saying that the dead load, live load are dependent on the floor plan and the general loadings that you may have. So those are usually constant, and the seismic weight therefore is also constant because seismic weight is dead load plus some percentage of live load. Now he's saying that if we increase the shear walls from 4 to 8, the structure obviously becomes stiffer. So if your structure becomes stiffer, let's say instead of 4, you had 8 walls along X. Okay. So maybe something like this you had. So for a 8 walls for a system configuration with 8 walls, naturally the time period, let's say for 8 walls, will be lesser than time period for 4 walls. I hope all of you understand this. So because the walls will add stiffness, so time period naturally for 8 walls will be lesser. So what will happen that the AH for 8 walls will be more than the AH that you get for 4 walls. Why so? Because generally we know that the SA by G curve with respect to time period of your structure is like this. So with increasing time period, the SA by G reduces or the spectral acceleration reduces. So for shorter time periods or for stiffer structures, you will have greater values of AH. So if you have greater values of AH, I mean, for 8 walls, you will have greater value of AH. So now his question is, if we increase shear wall, why are we designing for higher forces? So he's saying that we are putting 8 walls, then why are we penalizing ourselves by designing for higher forces? So see, the answer is very simple. You have to understand that seismic forces are not actual forces. They are sort of a resistance that your structure offers resistance that structure offers to ground motion. Okay. So there is no earthquake force acting on the structure as such. What is happening is your ground shakes and your structure tries to resist that shaking because of the inertia, and because your structure has certain inertia and the ground is exciting. I mean, ground is the ground motion tries to excite your structure and structure offers resistance. So earthquake forces are not actual forces, but they are the resistance that your structure offers. Now, obviously, if your structure is stiffer, it will offer more resistance, isn't it? You could, uh, let's say, understand it this way, that if you have a large tree, okay, and if you have, let's say, a small thin shrub, naturally, if there were some wind forces acting, I'm taking the case of wind force, you will understand it, uh, because you have seen the trees shaking under the wind effects. So let's say if there was a wind acting, which of these will have a tendency to fall first? So maybe the situation will be that a large tree falls easily than a flexible thin shrub. Why so? Because the flexible thin shrub will have tendency to will have a less inertia, so it will just oscillate or just vibrate with the wind forces. While a tree, because it's so stiff, it's so large, it may not have the same level of oscillations, and it will attract therefore more forces, and it may have a tendency to fall down. So same thing happens over here also, that a structure which is having 8 walls, because it is stiffer, it will attract more forces, it will have more inertia, it will attract more forces. So now the question is, if we are getting penalized by designing a structure with 8 shear walls for more forces, why at all to add 8 walls? Why not to live with 4 walls? Isn't it? Why not to have a structure with 4 walls only? Why to add 8 walls? So the answer to that is also very simple. We need to control deformation and displacements, isn't it? Because you are thinking in terms of force controlled behavior, that's why you have this confusion. But please understand that earthquake needs to be better understood as deformation controlled. Okay, so one important aspect that we need to control is the deformation, displacement, and therefore drift in your stories. So that will only be controlled when you have more stiffness rather than having a flexible system. Is this clear? Hello, are you getting this point? Also, because why you want to control the lateral deflections, another reason is because of that p delta effect, or the effect of gravity loads on your system which undergoes sway. So if the sway values are large, it will have the gravity loads acting on your system will have a greater impact on your structure. So that also you want to control. So basically the short answer is that although we are getting penalized by designing for higher forces, our intention is to make a structure more stiff and thereby be able to control the deformations and displacements also. All right. So I hope this answers your query. Then next question is, uh, where is the next question? Yeah. Next question is from engineer Vineet Kumar. He is a working professional from Patna, and he is asking, what are the important checks and best practices for modeling and designing a waffle slab in StatPro to get accurate and code compliant results. Now, what is a waffle slab? The waffle term actually derives from the waffle cone. I don't Have you seen waffle cones? Ice cream cones. So this waffle slab term actually gets derived from there, and waffle means closely spaced grid-like structure. So in the cones, have you seen waffle cones? I think if you go to Naturals ice cream, they give the ice cream in waffle cone. So there will be some grid-like pattern on the cone surface, ice cream cone. So similarly in the slab also, if you are going with a waffle slab, it will have a grid-like system. So there will be a lot of beams in both directions. So waffle slab is nothing but a grid slab. Okay, you call it grid slab, you call it waffle slab, whatever you want to call it. Basically, it means that you have a mat like thing where you have closely spaced beams in both directions, and because of the closely spaced beams in both directions, you are able to cover large column free spans with the help of a waffle slab like this. So now his question is, what are the important checks and best practices for modeling and designing a waffle slab? See, some of the things to be understood is that these types of waffle slabs work well. In my opinion, these waffle slabs work well when you have an aspect ratio is closer to 1. Okay, only then. What do I mean by aspect ratio? The, let's say, the long span to short span ratio. The green things are the columns at four corners, and Ly upon Lx is the aspect ratio. So these waffle slabs will work well when your aspect ratio is closer to 1. If you have a aspect ratio, let's say, which is approaching 2, then waffle slabs won't be very efficient, because then what will happen naturally, that the short span beams will attract more forces and the long span beams won't be that much effective. Okay, so provide waffle slabs when you have aspect ratio closer to 1, maybe around 1 up to maybe 1.25, it's okay. So this thing you should keep in mind. Then one more thing is that you have to have strong peripheral beams for that. Okay, so your peripheral beams should be strong. If your peripheral beams are not strong, by strong I mean they should be strong and stiff. They should be decent sized. If your peripheral beams are not decent sized and not stiff enough, this waffle system won't work well. Is my voice audible to all of you? The waffle system does not work well if your peripheral beams are not strong. That is the second point. So how would you ensure strength and stiffness? Maybe on the peripheral frame you may have more columns. Okay, see, waffle slabs you want because you want large column free spaces, but on the periphery you may plan for try to have more columns placed. Then this type of waffle system will work well. Another point I think is to check properly for the torsion effects. So because all these beams are interconnected and there is a certain sort of, there are no releases over here. So it's not as if you will be releasing this beam between these two main beams. No. So it's a all sort of rigidly connected system that you're trying to have. So check for torsion and uh, ensure that design for torsion is properly managed. Okay, then another point would be that what is this grid that you want to maintain. So this grid, or let's say this void that you want to maintain, how much you want to maintain, that is another point. Now, generally I have seen people maintaining around 1.5 to 2 meters as this grid dimension. So this may be this may also depend on some architectural considerations. So for that also need to be thought about. As I told you, generally 1.5 to 2 meters is a good grid spacing to maintain. Try to have same depths for all the beams in both directions, otherwise things will become very complicated. And I don't know what else. Yeah, one more thing, if you are going for Stat Pro, just try to have a plate model also for slabs, and then check, do two things: try a slab modeled as plate elements and then see what are the effect results you are getting, and then another time just apply floor loads as we do in stat without modeling slabs, and then also see what's happening. So just compare these two results, because the slab offers a lot of stiffness in these waffle systems. So just do that comparison once: a waffle slab without modeling the slabs, I mean just beams and applying the floor loads in StatPro, and a waffle slab where you have also modeled the slabs as plate elements. So do these things. I think this should be a good starting point for you. And I'm not sure what you mean by code compliant results. What is meant by code compliant results? Code does not. I don't think code gives you um, gives you much about waffle slabs and their design provisions. I don't think so. Does IS 456 give you uh, guidelines about waffle slabs? I'm not sure. Okay, so these were my thoughts. Then next question is from engineer Ronak Kare. He is from Goa and he is a working professional. So he's saying, he's asking, he has a question regarding ETABS design workflow. So when we model a building in ETABS, we usually start by assigning uniform trial sizes to columns and beams and then run the analysis to obtain forces. Since these forces themselves depend on the assumed stiffness, how do we professionally arrive at the final varied sizes of columns and beams across different stories and spans? So what he's asking is a very practical question that see our what is our end goal of performing, let's say, design. What is the end goal of performing design? That we want to do the analysis for given loads, and as per analysis we want to find out the design forces. Okay, design forces, moments, etc. And from this we want to finalize the sizes, isn't it? This is how, or let's say this is our end goal, that finally we want to have the sizes, and we want to, obviously, sizes and reinforcement both we need to sort of get by the end of our design process, and that is what our end goal is. Now the problem in softwares is, or problem with indeterminate structures is, that you need to have the stiffness accounted for, otherwise your analysis will not happen. Okay, see, in our moment distribution method, our analysis changes with the stiffnesses, yes or no? And in the matrix method that softwares use, or flexibility method or stiffness methods, both are matrix methods. So in these methods, unless you give the size, the analysis won't happen. So are you understanding what the problem is? So the problem is that the final thing that you wanted, which was the size, this itself needs to be given as an input while running the analysis. Are you getting the problem? What he is trying to ask? That what was your end goal? You wanted the size of your RCC sections, or let's say even in case of steel members, you wanted the final sizes. But then, just to run the analysis, you need sizes as input. Otherwise, the analysis won't be performed by the software. And if the analysis is not performed by the software, you won't get the design forces and moments. And if you don't have the design forces, moments, etc., you won't be able to finalize the size. So this is a catch 22 situation where the expected output is itself the input for is itself the input for the starting step. You understand? So how to get about it? So basically we follow what is called as an iterative process. We follow what is called as an iterative process of design. So what we do is we start with some trial sections. So let's say I start with a beam section of, let's say, 300 by 600, okay, and a column size of maybe 400 by whatever 500, okay. Then I perform the analysis. This I assign in my model. I perform the analysis. Then I get the design forces and moments. Then for these particular design forces and moments for the given section, I check the section. Are you understanding this point? Hello. I check the section. Now, two things may happen. Let's talk in terms of utilization ratio right now. Okay, let's talk in terms of utilization ratio right now. So I have given a 300 by 600 size, 400 by 500 column size. I checked the section and I found that such a large size is not required, and maybe I can reduce it to, 300 by 500, and column size maybe 400 cross 400 is also okay. Okay, I find this out now. So can I stop at this process? Can I stop at this process? Answer is no, because I again need to go back and change this size now. Why change the size? Because as you know that the analysis results are stiffness based. So I will now change this size. Okay, and I will again run the analysis. Sorry, yeah, again run the analysis, get the design forces, moments, etc., and check for this size. Once I check for this size, again I may find that no, this further, maybe we may further have a margin of reduction. Why? Because when I change the sizes, my analysis forces also slightly got changed. So it may happen that I now may decide that I guess beam size may be revised and columns we may keep as it is. So now I go for next trial or next iteration, and then I will again follow the process. So how long will I keep on doing this process? I'll keep on doing this process unless a convergence is achieved between the sizes that we assumed for analysis and the final sizes that we got after checking for all the design forces, moments, deflections, etc., etc. So this is the sort of design iteration that you have to follow. Is this clear? And this you have to keep on doing unless you are able to converge upon the sizes and the sizes that you took in analysis. Till the time you get those sizes appropriate and are able to check for the design results also, till then you will have to do these iterations. Now therefore, what is the difference between, let's say, an experienced engineer and a person who is, let's say, starting, who is a fresh engineer? What will be the difference? The difference will be in these number of iterations. You understand? So maybe an experienced person. So it's, yeah, one more point over here. Another thing may happen, that let's say you started with 300 cross 600, you did the analysis, and after design, when you checked, you saw that no, the sizes are not sufficient in the analysis, and I need to increase the sizes. This may also happen, that the initial size that you took, it was not sufficient and you had to change the sizes. So if that happens, again you have to go back, run the analysis, do the design, do the get the design forces, moments, etc., again try to uh, see and check for all these design effects, and then again you may find that no, further size needs to be increased. So either your initial chosen size is less than required, or your initial chosen size is more than required. In either cases, you are required to do the uh, iterations to achieve at a optimized and safe result. Is this clear? So the difference between an experienced person and a fresh engineer might be that an experienced person may have to do less number of these iterations. Why? Because from experience they know that if this is the span, this is the loading, this is the type of structure, maybe this is the seismic zone, or maybe this is the wind location, then a certain size should be good enough. So an experienced person may require lesser number of these iterations, and a fresh person or a fresh engineer may require more number of iterations. But both have to follow this iterative process of design. Is this clear? Okay, good. I hope this answers your question. So, professionally, how do you arrive at final sizes? By doing iterations, and then many times the sizes are a function of the architectural requirement also. You may have to ensure that the sizes that you are giving are suitable for architectural or for other processes and other uh, trades. Sometimes according to the mechanical requirements you may have to finalize certain size, whatever. Okay, so this is the iterative process that you have to adopt and follow. So this was Engineer Ronak, and these were the questions that were asked on the Google form. There are no questions on WhatsApp, no questions on email. So now I'll go and take the queries from the live comments. Okay. So the first question in the live comments is Sandy. Mr. Sandy is asking what is the difference between moment connection and main difference between shear connection and moment connection. If a connection allows, if a connection resists only shear and allows rotation, then which connection will it be? Tell me. Anyone from the live audience? I'm saying if a connection resists only shear forces and it allows the members to rotate at the connection junction, then which type of connection will it be? It will be, generally it will be called as a shear connection. And if a connection allows, or if a connection resists, instead of calling it as shear, I'm saying if a connection resists only translation, that is displacement, and allows rotation, then we are calling it as a shear connection. And if a connection resists translation as well as rotation, then we call it as moment connection. Is it clear? The basic, let's say, basic definition. So this may be understood better in for steel members. So let's say if you have a column, I'm showing you the elevational view, and this is your beam. And generally, what happens is that the in a this is I section. Both are I sections that we have taken. So generally, what happens is that in I sections, the moments are transferred by the flanges, because this is how the stress distribution in flanges look like, and shear mainly is transferred by your webs, because this is the shear stress distribution across the cross section. So if I wanted to have a shear like connection, what I will do is I will only try to hold the web, and then there can be various ways of holding the web. So to the column flange, let's say I'm only holding the web portion of this beam. In such a case, this can be close to being called as a shear connection. Why? Because it is resisting the downward translation. So that's why it will generate shear forces. But it is allowing rotation. There is no rotational restraint because you are not holding the flanges. So this type of connection can be called as a shear connection. In moment connection, what we will do is that we will, in addition to holding the webs, we'll also try to hold the flanges of this beam, because we want to restrain the rotation. And to restrain the rotation, I will try to hold the flange also. So I am holding the web also by whatever connection system. There can be multiple options of doing that. And let's say I'm holding the flanges also. So I may call this connection as a moment connection. Are we clear? Now in moment connection further, there can be a situation where the rotation is not fully restrained and there is some relative rotation happening between the beam and the column. What do I mean by relative rotation? So before the load application, let's say the angle between beam center line and column center line was 90. Now after the load application, the beam deforms. Column also deforms because column and beam together in a portal action. So column also deforms. But while this deformation, what is happening is that the final angle that I get is less than 90 degree. Suppose. So that means what has happened? That relative rotation has happened between beams and columns. If that is the situation, then I call my connection as semi-rigid. Please understand. And in connections where the relative rotation remains the same after displacement, that means before the load application the angle was 90. After the load application the system rotates, but the rotation is such that the relative angle still remains the same. So those kinds of systems I call them as rigid. So in moment connection there can be further two, let's say, classifications. One I can call them as rigid connections, and the other I can call them as semi rigid. And if a connection has no restraint to rotation at all, then I call it as a shear connection or a pin like connection. Clear? So these are the usual connections and how they get defined. Okay, good. Next question is from engineer Santosh Kumar Nirmalkar. He is asking gravity loading बिल्डिंग डिज़ाइन में एडिशनल मोमेंट क्यों आ रहा है और इनको डिज़ाइन में लेना चाहिए या नहीं, इनका कोई सॉल्यूशन, पी डेल्टा लगाने से ये बंद क्यों हो जाता है. See, under the effect of gravity load, what ETABS does is that in ETABS, it calculates for column design. What ETABS does is, and let's say I'm talking about IS 456 right now. So it calculates the Q stability index. If that Q is greater than 0.04, I think is the limit, then it takes the effective length value K for sway frames. So there is a alignment chart based on the which chart do we call it as? The Moreland alignment chart, I think. The Moreland or Moore or something alignment chart. So then based on the K values for sway columns, so there are two tables or two figures rather. One figure is for sway columns, one figure is for non-sway columns. So if your stability index Q is more than 0.04, the K value for sway frames is considered. For K factor calculation, ETABS calculates the relative stiffnesses at two joints, top and bottom joints. Okay, so this it calls it as beta 1 at one end, and similarly beta 2 again you will calculate at the other end. And for these betas, beta 1, beta 2, there will be this kind of a table, I think like this, something, alignment charts. And for beta 1, beta 2 value, you basically have to plot the beta 1, beta 2, and from here you get the K. For this K, then you will calculate the additional moment. So there is that formula given, I think PU upon 2000. I'm not remembering the formula correctly right now. Maybe something like this is the formula. So over here, the length then needs to be taken as the effective length, and this will be K times the unsupported length. So this L effective gets put over here, and then this is formula something like this, if I remember correctly. And from here you get the additional moment, and then for that additional moment you need to design your column. Suppose your Q is less than 0.04, then the condition is called as a non-sway frame. For non-sway frames, You need to find out the k as per the figure given for non-sway frames, and that k then you need to use for calculating ma. Now what happens is, what is question is that if I am designing a building only for gravity loads, technically there is no possibility of sway. If there is no possibility of sway, then why is ETABS still uh, calculating very high additional moments? So for that, you just check the Q value being taken in ETABS. Just check what Q value is being calculated by the software. It has been seen that sometimes ETABS erroneously, that means incorrectly, calculates very high Q values. So even in the analysis manual, this statement is given that it is seen that sometimes ETABS does an incorrect Q value calculation, and it will give you, let's say, Q 0.042, or Q value calculation may not be very wrong sometimes. Q value may be correct, but sometimes erroneously it calculates very high K values. Let's put it this way. So Q value calculation may be still okay, but you will find, or you will see, that the K value calculation is giving you absurdly high values. Okay, so maybe for a very a Q, let's say 0.042, just sway frame, still the K may be 5, 6, 7 in that region, and because of that, very high additional moments are getting assumed by the software for column design, and therefore you might get very high column reinforcement percentage. So this is a common problem that is seen. What is the solution for this? So solution is, you take a decision as a structural engineer, and let's say if your building is not in a very severe seismic zone, okay, let's say zone 2, and not a very tall building, so it's not very crucial, and because the zone is less, you also don't expect a lot of lateral sways, and if there's not much lateral sway, the effective length calculation is not very important, I would say. So in such cases, you may artificially override the k value and design it for at least 1.2. So if you refer to the annexure E, if you refer annexure E of IS 456, which tells you about the effective length of column, it suggests you to take the minimum k as 1.2. So you may take this k as 1.2 and then accordingly do the design. Okay. His next question is, P delta लगाने से बंद क्यों हो जाता है? So the answer is that these additional moments basically consider, or they basically are called as first order moment magnification process, where we are not analyzing for the actual deformed geometry, and because we are not analyzing the structure for actual deformed geometry, we are artificially magnifying the moments by these formulae. So this is called as the moment magnification approach. Your ACI code also calls it as the moment magnification approach. IS code does not call it as the moment magnification approach, but that is the uh, general, let's say, principle behind these additional moment formulae. So when you apply P delta, basically what you are doing the second order analysis, and when you do the second order analysis, you are considering the deformed geometry, and when you are considering the deformed geometry, you are basically accounting for the sway effects in the analysis itself. When you do a P delta analysis, you are considering the second order analysis, you are doing the second order analysis which considers the deformed geometry, and basically you are considering the sway effects as well as the member effects along the length. So because P delta has been run, then the software will not take any k value. It will say that because you have done the P delta, so you need not consider the additional moments now, and you be happy with the P delta analysis results. So that is the reason why when you include P delta analysis, then the software will not consider the uh, K value calculations. Do you understand? It will, I'll just repeat, I will just slightly correct myself. So it will not do the K value calculations, but it will still do this additional movement because this is what is called as the P small delta effect. So for P small delta effect, it will still do this formula use, but K value calculation it will not do, and it will directly take a K of 1 because the sway effects will be considered in the P delta analysis itself. So therefore, if you read the ETABS manual also, it says that the software or the code, sorry, the it is expected that as a user you run the P delta, and when you run the P delta, the K value will be taken as 1, uh, and then you just need to consider this additional movement formula for the P small delta effect. Okay. All right. So I think this question has been answered, and yeah. Good. Next question is from Engineer Arjun Srivastav. He is asking, when I make fixed base plate, sometimes I get very big size of plate. ड्राफ्ट्समैन बोलते हैं ज़्यादा बड़ा size है according to the bolt. Now, what do you mean by size? You mean the plan size or the thickness? What do you mean by size? I think you are getting large thicknesses, or you are talking about the plan size. Length and width. No, so why are you, I mean, how are you calculating the length and width of the base plate? What is the process that you are using to calculate the length and width of the base plate? How do you calculate? Say this is the column and it had certain moments, and how do you calculate the length and width of base plate? So see, if you are getting more, maybe you are getting more length and width, that means that is indicating that the bolt forces that you are having are very large, because of which you need to further increase the lever arm, and further increasing the lever arm means increasing the base plate. Web plus 200 extra for the bolt. That means from here you are getting 200. Is this what you're saying? See, generally, if you, let's say, give it some 50 and keep this as 50, I mean, around 100 or 125 is a good distance to have. Okay. 100 to 125 is a good distance to have. And within that, usually you will see that the sizes get satisfied. Now, if your sizes are not getting satisfied, that basically indicates that your bolt forces are more than the capacity. So your options are then either to have more bolts. When you have more bolts, what will happen? That more bolts means the forces in each bolt will reduce. So by that way, you will be able to control the uh, deformation of the, sorry, you will be able to control the size of the base plate. Also, one thing you can try and do is to change the thickness. Now when we change the thickness of base plate in our hand calculations, usually the thickness of base plate thing does not come into picture, because we usually don't do the calculation as per the base plate thickness. So that thing usually is not accounted for in our hand calculations. But let's say if you were to use a software like Idea Statica, which incorporates the stiffness of base plate also, then you will see that when you make your base plate thicker, the force distribution in the bolts gets uniform. Otherwise what happens is that for thin base plates, system is flexible, so the bolt forces might be absurd in the outer bolts and almost very little forces in the inner bolts. So for that, you should try to go for some thicker base plates and also try to provide stiffeners. This will improve the stability of your stiffness of your system, and the bolt forces will become more uniform. So to reduce the plate size, my suggestion is to add more bolts and go for a thicker base plate. Uh, and then you will see that within this, let's say the general guideline is that you keep around 58 to 75 between the face of your member to the bolt center, and another 50 to 75 from bolt center to the base plate outer. In these dimensions, usually your base plate size satisfies. Okay, क्या हम दो लेयर ट्राई कर सकते हैं लेंथ में bolts? Yeah, you can do that. So if you see, look at the pre-engineered sheds and the general detail that these pre-engineered shed fabricators adopt. If your column is I section, the general bolt layout that they adopt is something like this, where they give bolts in two layers like this. I don't know if you have seen this type of an layout. Okay, so they don't give bolts in the web portion anyway. They will concentrate their bolts in the flanges region like this. So this you may give. All right. Good. So this was Engineer Arjun with his query. Any other query? N Raj 2597. Okay, Arjun is asking flange के बाहर अगर करे तो you can do that as well, but the effectivity will be more if you follow this what I am showing you. You want two layers outside the flange, it won't be very effective, but you can do that. But to increase the effectivity, you should try to do this type of a thing on either side of flanges. Yes. Okay, good. Then NRAJ Raj 2597 is asking when can we expect your new course on IS 1893-2025. We'll do it. So right now at present we are doing a course on RCC design as per ACI 318. It's a good course that we are doing, which includes ETABS, STAD, sorry, not STAD, ETABS, SAFE, and manual calculations. So once we finish this course, then we will start the next course that we will do will be on the uh, earthquake analysis design. I think the design has not been, the design codes have not yet come. Let's say the earthquake calculations and analysis as per your newly launched codes. So I think they have done a part 1 and part 5 now, right? We have got two parts now. So both will have to be included in this course. We will do it something like this. Okay. I was just waiting that maybe if they launch the 13920 also together, so we will be able to cover both the EQ calculation, analysis, and design aspects. So I was hoping that the IS 13920 also gets revised and we will be able to do an integrated thing. Have they given any timeline for the revised 18930? Sorry, 13920? Hello. Is someone aware about it? Any timeline that the BIS committee has given for the revised 13920? Okay, I think the live audience is not aware. I'm also not aware. So let's wait and watch what happens. I think they're saying 13920 11 parts. I don't know when they come up with the next part. Anyway, so these were the questions that we conducted on this weekly session. Yeah, so am I audible and visible? I think there was some technical issue. Is my voice audible? Quick yes, no, please. All right, I hope I am audible now and visible also. So these were the queries that were there on this week's episode. Any other question? Okay. So the link for the Google form remains the same. As you all know, every week we meet on the weekend and conduct this live session. But throughout the week, you can put your queries. The Google form for which remains the same. So I'll just put the Google form over here. Oh, there is one question. Okay, wait. There are a couple of questions asked on the email. So let me take them up. Uh, where is it? Okay, so two questions from Engineer Raghu. Yes, I just saw your queries on the Gmail. So two questions. One is asking, in ETAP safe, the moments for envelope load cases are very high. Uh, I hope you are not meaning load cases. You are saying load combinations. What I understand. So you're not talking about load cases. I'll just correct you over here that I believe you are asking about load combinations. So he's saying that the enveloping load combinations results are very high, and checking the individual load combination shows much lower values. Can we therefore consider only the individual load combinations instead of envelope combinations? Of course, that is what is expected. So we don't design for envelopes. Envelopes are only for to get a good, I mean, just to get an idea of what's happening. Otherwise, you are expected to design for individual combinations in the envelope. So maybe you may have several different combinations, and this statement that I just made, this may not affect, let's say, cases where your actions are not linked to each other. For example, in beams, the design for movement does not depend on the shear values, isn't it? Or let's say the shear design does not depend on the moment values. But if you are doing a design, let's say in case of columns, where the combined effects of axial forces and moments have to be incorporated in design. Then taking the values from enveloping combinations is incorrect. Okay. So what might happen is that for different load combinations, let's say I'll just write down, let's say axial force mu and maybe mu2, okay, something like this, and maybe it's a case of column. So for one combination you are getting axial load of 600 kilonewton, moment of 95, and about the other axis for other load combination maybe this kind of an axial load and increased moments, just some hypothetical values, okay, and another load combination this type of an axial force and maybe this type of moment. Is Are you able to see the results? So if you do an envelope thing, you will end up taking which values for design? If you do it as per envelope, you will take the maxima of all load combinations. So you will take this, and this, and you will design for 800 kilonewton PU, MU3, M33 of 120 kilonewton meter, and M22 of 25 kilonewton meter. So you may end up designing for this, which is incorrect because these actions are not going to occur simultaneously. So what you need to do is you need to perform your design three times. That means you check from the envelope, let's say you check which is the highest axial load. So you get that the highest axial load is 800 kilonewton. So then instead of taking the enveloping values, you take the corresponding M33, M22 for the same load combination. So you perform your design once for this combination of axial forces and moments. Then you check for which combination you are getting the highest M3, let's say. So you are getting for this. So then you consider the corresponding, that means in the same load combination, take the other two values and perform your design twice, two times. And for the other action again, perform the design three times. So taking envelope values is incorrect. And as I told you, this is crucial, especially for those members where there is an interdependence or interaction between different actions. So for example, in case of columns, or for example in case of foundations, if you are taking envelope values, it's a problem. Why it's not such a big problem in case of beams? Because as I told you, if you are getting some hogging moment and you take the enveloping hogging moment and just design for it, the hogging moment value will not impact or depend on the, or it will not affect the design for sagging moments, isn't it? Or the hogging moment value will not have any effect on the design for shears. So for beams, it does not matter as such whether you take enveloping values or not. But for members like columns, footings, where there is an interaction between different actions, taking enveloping values is incorrect. Good. Then his second question is the geotechnical report indicates liquefaction potential at 5 meters below ground level. How should this be incorporated in analysis and design, and how to account it in SAFE? I don't know. I have never tried. Maybe in SAFE and ETABS, now you have the option of modeling soil. So maybe some at that level, let's say 5 meter below ground level, you may have to model the soil layer and provide the C5 values, and maybe under the earthquake effects, maybe provide the uh, corresponding C5 values expected under the effect of liquefaction. Maybe that sort of a thing you might have to do. Although I have not done it myself, so I don't know much about it. Generally, what we do is if your soil has a tendency of liquefaction, then we generally try to take our foundation systems below it. So it might happen that let's say this is your NGL and there is a certain strata or a certain zone which is prone to liquefaction. So if that is the situation, then you will not have your let's say footings at this level, or imagine that you're providing piles. So I will not terminate my pile in a zone which is prone to liquefaction. In that case, I may have to go to deeper depths which are not prone to, or I may have to rest or go till this strata which is not prone to liquefaction. And then in capacity calculations, I will have to ignore. Let's say this was a case of friction pile. So this strata of soil will undergo liquefaction. So I will ignore the friction that will be offered by this zone, and accordingly I will calculate what is available to me, assuming that this zone has undergone liquefaction. So I calculate my capacities disregarding the resistance offered by a particular soil strata which is expected to undergo liquefaction. So this type of thing, usually you will get assistance from geotech engineers, and they will help you with this. Okay, very good. So I think that's all for this week. Then you can stay in touch and ask your questions on the same Google form. And once every week, when we meet, we, as you know, we take up your queries. So I'll just put the link for Google form over here. Where is it? I'm just looking for. Yeah, thank you. This is the Google form which you can use. Okay, and then what else? And if you want to connect with us on WhatsApp, then you can click on this link. Where is the link? Uh, I'm just searching for the link. Wait a minute. Yeah, so this is the link for connecting us through message on WhatsApp. So you can click and send a message if you want. So I think that's all for this session then. Thank you very much. And thanks for joining. And see you next time now. Till then, have a good week. And we will meet you in the next session now. Bye bye.